Okay, today we'll see the sixth topic, deflections in statically determinate frames. Deflections in statically determinate frames using strain energy method. Strain energy method or unit load method. Now, in strength of materials, deflections of beams we have studied using Macaulay's method of double integration, moment area method, strain energy method. Then you have conjugate beam method. There are many methods to find the deflections. For a moment area method, if I values are different in different lengths within a span, then you will use the uh, moment area method. If I value is constant, you use a double integration method or the strain energy method. If the bend moment expressions are simple, then you can also go for the strain energy method like that. There are many methods we have learned. Now we will take now strain energy method to find the deflections in the statically determinate trusses. Why not indeterminate trusses? Indeterminate frames, let us say. Then first you have to find all moments, reactions. That itself will take half an hour time. After finding the additional unknowns, only then you can find the deflections by taking the strain energy method. That means because of the time, it will take 1 hour time to solve or to find the deflections in statically indeterminate frames. So they ask you in the exam statically determinate frames only, because support reactions you can find by inspection itself, or at the most with simple calculation you can find the reactions. Then directly we can use the strain energy Benjamin expressions, you can use it, and in the stipulated your 1 minute time or maximum of 2 minutes time you can complete the problems. So here only our scope is for statically determinate frames. You must use only strain energy method to complete within 1 minute time. Okay, so now let us see the concepts. Strain energy stored due to axial loading I have given you. Axial loading is potential, you can write in terms of complementary energy, summation of p square L by 2ae. If you write it, it is called complementary energy. For determinate structures, complementary energy, strain energy same, so we take as if it is also strain energy. If strain energy is written in terms of the deformation delta square ae by 2l, then that is called strain energy. Okay, then complementary energy has no physical meaning, it is simply a mathematical expression. Now we use the strain energy method to find the statically deflections in statically determinate frames only. So energy stored due to axial loading we have studied, energy stored due to bending moment also sir might have told you, integral of m square dx by 2ei. Let us see that expression I will write. Strain energy stored due to bending moment u is equal to integral of mx square dx by 2ei. How to get this expression? Sir might have told you, if you have a simply supported beam, say, you take a elemental length dx. In that again you take elemental area dA. So dA into dx is small cylinder type element, we take it. On that compressive stress upon neutral axis, if I take it, compressive stress is constant, you will take. Energy stored in that small element is integral of f square uh, we have learnt about the energy stored F square by 2E into volume. So F square by 2E into volume, volume means dA into dx. So double integration we take it. One integration is along the length, one integration along the area. So double integration when you take it, integral of y square dA you will get. So one integration will be removed, integral of y square dA. dA into y square means it is the second derivative of the second moment of the area called moment of inertia. So now I think by this wording you might have recollected what sirs might have told you regarding the strain energy stored in a simply supported beam. How we have to derive F square by 2E into volume if I take it for an element and double integrate m square dx by 2EI you will get. Okay. Now second point is from Castigliano's theorem 2. Theorem 2 is applicable, you can apply to determinate or indeterminate structures, they must be but linearly elastic. So we are taking linear elastic structures only. Displacement delta is equal to, delta is nothing but displacement, is first derivative of energy with respect to load at any point in the structure. So there must be wherever you want to find a deflection, as in the strength of materials, there must be a load. If load is not there, you sir might have told about you consider one dummy load or pseudo load whose magnitude is 0. So like that, if load is there, fine. Otherwise, some other load W whose magnitude is 0. So dou U by dou W, displacement at any section. So first derivative of energy, if I take this one in mx square means 2mx into dou mx by dou w into dx by 2ei. This we write it as delta is equal to 2 cancels out mx, dou mx by dou w you take it as m. Similar to pkl by a you have written for the axial loading strain energy. P means forces in the members, k means forces in all members again due to unit load, L by AE. Similar to that, you will get dou mx by dou w means the meaning of dou mx by dou w is bending moment at any section due to unit load applied at a point where you want to find the displacement. So that we represent it as m, mx into m dx by EI, where mx means bending moment at any section xx due to applied loads. Then m means this is actually dou mx by dou w. Implied meaning is bending moment at the section xx due to unit load. Unit load applied at a point, applied at the point where we want to find, displacement. Like that. So in 2 minutes time, first you have to find mx, then due to applied load, due to unit load, second step, then third step multiply. Similar to pkl by AE, you have mxm dx by EI. There axial rigidity, here flexural rigidity. Now here integration is there, integration of dx is nothing but L. So mx is similar to P, m is similar to K, integral of dx is similar to L. EI due to bending, EI due to axial force AE. So similar to pkl by AE, you have mxm dx by EI. Okay, that way you can remember also things easily. Now if you want to find slope at any section, slope at any section is equal to theta. If you want to find, first derivative of energy with this slope means is angular displacement. When you are finding angular displacement, there must be angular force. That angular force is moment. When you apply when you want linear displacement, there must be linear force. That's why there is W, there is M here. So slope at any section is theta is equal to dou U by dou M. First derivative of moment, first derivative of the energy with respect to moment at the section. So if at all at any section, if there is a moment already existing, fine. If it is not there, you assume an imaginary moment m whose magnitude is 0. Then differentiate it. Okay. So dou u by dou m. So mx square means again 2 into mx. Then this value will become dou mx by dou m into dx by 2ei. Like this. So 2 cancels out. I can write this as mx into m dx by ei. See, formula is same, but finding m values is different. M is because of a unit moment, where here mx stands for bending moment at xx due to applied loads. M means dou mx by dou m is not, whose meaning is like this: bending moment at the section xx due to unit couple. You have to apply unit couple. Unit couple means magnitude is 1 and it has no units. Due to unit couple applied at the point where we want to find slope. See, mx m dx by ei, here also mx into m dx by ei, formulas are same, but finding small m is different. Similarly to the trusses, 3 problems we have taken: pkl by ae. P is same, but k values are different. If you want to find only displacement, k means forces in all members due to single load. But if you want to find relative displacement, means the sum of two displacements if you want, you have to apply two unit loads either towards or away. That's all. Then find the k values. You will find k values because of two unit loads. But if you want to find a rigid body rotation of any member, you must apply unit couple at the ends of the members. 1 by a and find k values. So pkl by ae is same, but finding k values due to single unit load, due to two loads, or due to a couple, like that. Similar, but here only two problems. You can find the displacement, linear displacement or angular displacement in a structure. Okay, so that's what we have to do now. Now we'll see the numericals on this topic. You have a 2 marks question on this one. You will have to complete at the maximum of 1.5 minute time. Let us see how we should manage the problems. Slope at C is, assume that we have a cantilever frame like this. This point, let us say A, B, C. For a cantilever beam, already strength of materials you have studied. If you attach one more member, it becomes a cantilever frame. 2 marks questions means only 2 members will be there. 20 marks questions means one more member they will add. That's only difference. Okay. Assume that we have applied a moment of 10 kilonewton meter. This is a 4 meters 2I, 2 meters I. So this is the problem. First we'll write what is the scope of the work. That means what we are expected to do in the exam in 2 minutes time. That will give us a better clarity, better control over the exam problem and also on the time. So slope at c, theta c means integral of mx into m dx by ei. Now where mx stands for bending moment at xx due to applied loading. M means bending moment at xx due to unit couple. Unit couple where you have to apply. Since you want to find theta c, it should be applied at c. This is the scope. So first step is you show the in the diagram how to find mx and m values. Second step, multiply them. So this is the solution. First step, mx and m values. Supposing that if you take this as the cantilever member, this point let us say A, B, C. This moment is 10 kilonewton meters. This length is 2 meters, 4 meters. This you can take say mx diagram. Means for finding mx diagram, this is mx diagram. Next, you due to unit couple. You can apply now 1. That's all, only 1. This one has no units due to m alone. This is small m diagram we can write. Mx and m diagram. Okay. This point now A, B, C. Now you see mx values. Now you have two segments BC, AB. So in the two segments you have to calculate mx, m, multiply them. Not more than 2 members will be there because you have only 2 minutes time in the exam. Wherever you take a section xx in the applied load, same you have to take here also, section xx. This is at a distance of x we have taken, let us say. Now this is also x. So for this one and for BA member, you can take a section xx here at a distance of x. It is not necessary from here also you can take. For the given member, our choice to take a section xx measuring from A or measuring from B. Or BC also, you can take section xx at a distance x either from C or B. Whichever gives us a simple expression, that we will take it. In this case, you start from this end, you have taken. Otherwise, if you take support reactions also say for cantilever beams or frames, when you know support reaction, you can start from here also. Result will be same. But thing is, extra you have to find the reactions. So mx diagram, m diagram. Then second step is theta c is equal to integral of mx m dx by ei. Now the table should go like this. Member mx m, then theta c is equal to integral of mx m into dx by ei. Sign conventions are our choice. Whatever way you want, we can take it. Now sagging bending moment you take positive, hogging bending moment you will take negative. To suit to your sagging positive, hogging negative, you could stand here, look this way. Section right side anti-clockwise, it will sag the member. Okay. Same thing if you want to find force in this bending moment here to detect whether it is sagging or hogging, stand here, look this side. Okay, always you stand inside the frame, and if you take sagging or hogging, it will tally with our already learned sign conventions for bending moment. Here also same thing. You stand here and see whether movement is producing sagging bending moment or hogging bending moment. Okay. Now when you take a section XX here, here also same way you have to take section XX. Okay. Stand here means stand here, look right side. Stand here, look right side. That way. Now stand here means this frame. You go to the frame, stand, go here and stand like this. Now section right side anti-clockwise. It will sag the member. So it is sagging positive, hogging negative, you can take it. Member CB. CB member. What's the bending moment at XX? 10 into X or 10 into X square by 2. If you see that, when you have a moment itself is acting on the beam, let us say, you should not multiply with distance again to get the moment. So we should not write 10 into x or 10 into x square by 2, 10 itself. So section right side bending moment is 10, that's all. You should write it as 10. Sagging, so plus 10. Then small m. At the same section due to unit load alone. Here unit load means unit couple here. Go here means come here, stand here, look right side. Section right side anti-clockwise. Also again sagging, it will sag the member. So plus 1. So mx m dx by ei. Generally in the exam the integration will be such that by inspection you can write the values. So integral of 0 to, what are the limits for CB member? 0 to 2 mx into m into dx by ei. So 10 into dx means 10 into x, x means 2. So 20 by ei. This is, what is the 20 by ei is the contribution of the member CB to the rotation at C is 20 by ei. Similarly, what is the contribution of AB member to the rotation at C? Individual contributions, if you add it, you will get the total rotation at C. Next, BA member. Now, BA member means you stand here. Now you have a choice to look left side or right side. So section, you should not stand here, because when you stand here means here also you have to stand here and look down, and reverse direction you have to see. So you stand here, that means go here and stand this side. Stand here, look right side. Section right side anti-clockwise. Again it will sag the member. So plus 10. How to know plus 10? Because 10 itself is the moment. So 10 into x we should not write. So plus 10. Now stand here. This is the distance x. Section, that means you are standing here looking right side. Section right side anti-clockwise. Again 1. So plus 1. Okay. Now, so mx_m. Limits of integration are 0 to 4. Mx is 10. M is 1 into dx by e. I value have to be careful. This is 2i for the member AB. So 10 into dx means 10 into x is 10 into 4, 40. 40 by 2a means 20 by ei. So what is the total rotation you will get is theta c is equal to 40 by ei. Here positive sign, if you get it, it means that the theta c, the rotation, is in the direction of unit movement you have applied. Because again, in this case, there was a moment acting at c in the same direction you have applied unit movement. Supposing that moment is at one place, you want to find rotation at some other place, say. So at some other place in the unit moment, what you have given, in that direction it acts if it is positive. Opposite means opposite to the direction of unit moment if you get minus. Okay. So you get theta c is equal to 40 by EI. Now here positive sign indicates that theta c acts in the direction of unit moment. So theta c is anti-clockwise. So anti-clockwise rotation. Now next question, moment we are applying here. Now we want to find horizontal displacement or say vertical displacement of C. Here itself, this is over. Fresh problem you write it. Don't disturb this diagram. Draw a fresh problem. Now the question is like this. Delta vertical displacement of C. This how much? Problem same. What you have to change here in the note? We have to find now delta vertical displacement of C. Formula is same, mx m dx by EI. Mx is same, bend moment at xx due to applied loading. M, bend moment at xx due to unit vertical load you have to apply. Due to unit vertical load applied at C. This you have to be careful. Now this is your scope of the work. Let us come to first step. Mx and M values. Mx diagram, this one. Mx same, but M value you have to change. Now you have to apply unit vertical load like this. 1. This one has no units. You must draw a second diagram. Fresh diagram you have to start. Take the problem. Take this one. Whatever changes we have made, you must write in your notebook a separate problem. Don't disturb the earlier problem because it is independent problem. In the exam, any one question they will ask, either slope or vertical displacement or horizontal displacement. So mx diagram same, m diagram same. Here you have to change. This is delta vertical displacement of C. Okay. Now if you come to this one, this we can, I remove it. Okay. Now table also same. Again time allotted is also same. 2 minutes time. Quickly in say 20-30 seconds you must draw these two diagrams, mxm values, then multiply them like this. The integration will not take much time. Okay. Now mx values same, m due to unit load. See here, when you stand here, look right side, section right side anti-clockwise, you are taking sagging. It is a bending moment, not the simply moment. So anti-clockwise, negative, clockwise, positive sign convention won't be applied. Mx means bending moment, not moment. Okay, so plus 10 is over. Coming to this one, stand here, look right side, section right side or whatever side we take. Section, you have a downward force. Section right side, there is a downward force. Downward forces, whether they act right side or left side, they will always give negative bending moment. How much? Now you see this distance is x, minus 1 into x we have to write. This is the change, minus 1 into x. Minus because of hogging bending moment. Now when you integrate this one, you will get like this. Integral of limits of integration 0 to 2, 10 into minus x dx by ei. Minus you take it 10 common out, x means x square by 2. X square by 2 means 2 square by 2. So 10 into minus 10 into 2 square by 2 ei. So you will get minus 20 by ei. Next, this one. Stand here, look right side. How much moment? This total length is 2 meters from here to here. Now see bend moment at xx here, if when you want to find, how to find? Shall I take 1 into this x or 1 into this x? To find bend moment at any section xx on the cross section, you have to stand like this. Then travel from tail to the head towards the point. Like this you have to move. When you are moving it, you put your pencil or pen, whatever it is, on the line of action of the force like this. Then where your section xx is cutting the beam, you see beam or column, whatever it is. So from that dot to this vertical line, what is the distance? 2 meters. So 1 into 2 you have to write, not 1 into x. So this value you will get minus 1 into 2 because it is hogging bending moment. Now limits of integration are 0 to 4. Mx 10, m is minus 2 into dx by e into I. I means 2i. This always you have to be careful. 2 cancels out, 10 into dx is x. So 10 into x means x limits are 4. So minus 40 by ei. So now this value is also what we are finding is delta vertical displacement of c. So you will get delta Vc is equal to minus 60 by ei. So minus 20, minus 40, minus 60 by ei. Now when you come to this one, this I remove. Now delta vertical displacement of c is equal to minus 60 by ei. This is the answer. In this case, negative sign implies that delta Vc acts opposite to the direction of unit load. You see here, at that moment direction is different. Whatever direction unit load is acting, whether moment is there, applied moment we are not concerned. How you applied unit load? If you get positive result, that means in the direction of unit load displacement happened. If you get negative result, opposite to the direction of unit load, whatever may be the moment direction, clockwise or anti-clockwise. Okay, opposite to the direction of unit load, not applied load. So delta Vc is equal, delta Vc acts upwards. That 60 by EF, when you apply anti-clockwise movement, we didn't visualize that when you apply anti-clockwise movement, see, we thought it would go down. But negative result came, which means that it will not come down, it will go up. That's the implied meaning. Then we will realize that when you apply anti-clockwise movement, you will find that it goes up like that. Okay. Now, this is the second, delta Vc. Now, let us see, we want to find horizontal displacement. Here itself I will write it. You draw a fresh problem with the following arrangements. Whatever red color we have shown, that is the changes that you have to make it. Now, you see, next question is, what is the horizontal displacement? Horizontal displacement of C is, if you want to find horizontal displacement of C, here you have to write delta horizontal displacement of C. Formula same, mx same, but m is different. Bend moment at xx due to unit You have to write this one, unit horizontal load. This is the difference. Unit horizontal load applied at C. This is your scope of the work. Then first step, mx and m values. This will not change. This you should not keep unit vertical load, you must keep unit horizontal load. Now you see you have to apply 1 and again this one has no units. So whatever direction displacement you want, you can get it by applying unit load at that point and finding the moments. Now this one, delta horizontal displacement at C, formula same. Here you have to change delta horizontal displacement of C. Then this table we have to change. Okay, table is same for vertical displacement, horizontal displacement and rotations same, but this delta HC, delta VC, theta C, like that we have to write. Now coming to this problem, this is the table. Stand here, look at this one. Section right side anti-clockwise, plus 10, already written. Coming to this one, due to this horizontal load, what is the bending moment at the dot? Section XX is cutting the beam at the dot. So stand on the dot, look at the force. Travel from tail to the head towards the point. You will find that this force is passing through the point itself. So the perpendicular distance between the dot and the line of action of the force is 0 because resting on that. So 1 into 0. Don't have to worry whether it is plus 1 into 0 or minus 1 into 0. So once a small m becomes 0, this becomes 0. Now what is the meaning of this is CB member you have delta HC 0 means the contribution of the CB member to the horizontal displacement of C is nil. Now the member BC is axially rigid. Okay. So whatever, because of the moment M 10 kilonewton meter, whether you apply 10 or 100, member BC as a rigid body it will translate, it will not contribute to the horizontal displacement. Okay, that is the meaning of that. 0 means because of member CB, horizontal displacement at C is nil due to the applied moment of 10 kilonewton meter. Next, BA member. Stand here, look right side, this is plus 10 because sagging. Now stand here, look right side. Look right side means this one. Travel from tail to the head towards dot. Dot here, line of action of the force here. Dot is here, line of action is this one. So force into perpendicular distance means this x you have to write. Now you see section right side clockwise, it will hog the beam or member. So you must write minus 1 into x. Now limits of integration are 0 to 4 mx m into dx by e into I means 2i. So minus 10, x means x square by 2, that means 4 square by 2 into 2ei. So you will get minus 40 by ei. That means delta horizontal displacement of C is minus 40 by ei. Again, negative sign indicates that because of this moment m 10 kilonewton meter, joint C will not move right side, it moves opposite to the direction of unit load. Again coming to this one. Delta HC, you will get minus 40 by ei. Negative sign implies that delta HC acts opposite to the direction of unit load. Opposite to the direction of unit load. That is, delta HC is leftwards. Like that. Okay. So these are the types of problems. Not more than 2 members will be there in the exam. Now let us see how to draw the Bend-Newman diagram and the deflection profile. Note 1. Bend-Newman diagram and deflection profile. This is our beam, right? A, B, C. This is 2 meters, this is 4 meters, right? How to draw BMD? Quickly, no expressions should be written. Bend-Newman at x is so much, at x is equal to 0 so much, x is equal to L so much. We should not explain, even if it is a 10 marks question. Symbolically, one expression you will make it, one value will calculate, all others by inspection you have to complete. Even if it is a 10 marks question, you can complete in 1 minute time. Now you see, to draw Bend-Newman diagram for any member, what we have to do is stand here, look right side, section right side anti-clockwise 10, so plus 10. Stand here, look right side, again plus 10. If two places you stand and find the moment, if it is equal, it means that bending moment is a rectangle. That means it is a pure bending moment case. So, two places, even if you stand just to the left hand side of C and look right side, again 10 only. You cannot stand here and say section left side anti-clockwise, it will sag. It will hog, we cannot say. Section right side anti-clockwise, it will sag. But if I stand here and look left side, section left side anti-clockwise, it will hog. Then how to decide? This is the point. If you stand here, what will happen? We will fall down. So when we are falling down, whether it is rotating clockwise or anti-clockwise, you cannot detect. You must stand on the beam and look one side and decide whether it is sagging or hogging. Okay. Now, so two places when you stand and look this one, plus 10 you are getting. So this is the Bend-Newman diagram. 10 kilonewton meter, 10 kilonewton meter. Okay. Next. On the member AB, stand here, look right side. Section right side anti-clockwise. That means it will sag plus 10. Stand here, again see, same plus 10. That means here also it is a rectangle. Plus, this is 10 kilonewton meter, 10 kilonewton meter. Like this. This is your Bend-Newman diagram. Next, deflection profile. How to draw the deflection profile. This point, let us say A, B, C. When you applied anti-clockwise moment, it theta C anti-clockwise you got, C went left side. When C goes left side, B also goes left side. So B will go to somewhere here, let us say. B goes to B dash. Then there is a constant bending moment. Strength of materials you have studied that it bends like an arc of a circle, like this. Then here also arc of a circle. Because it is a rigid joint, 90-degree angle should be maintained as it is. So 90 degrees angle means it will go something like this. So if you drop a tangent here, 90-degree angle will be maintained like this. B will go to B dash. C will go to C dash. Now as we have learnt just now, delta HC is 40 by EI. That means minus 40 by EI you are getting. So this is your delta HC. Because it is minus 40, it is acting left side. So left side you have shown. Next delta VC. This value got it as 60 by EI. Upward it went. So again minus we should not write. Then theta C is 40 by EI. We got it. How to get that? At this point, if you drop a tangent to the curve, with respect to horizontal, how much it makes? Theta C is now you got it as 40 by EI. Anti-clockwise means like this. This is the anti-clockwise rotation. So this is a deflection curve. Now how will it bend? If a beam is subjected to constant bending moment, or if a beam is subjected to pure bending moment where m is constant, then the beam bends like an arc of a circle. So you get an arc of a circle here, two arcs of circles, this and this. These two are arcs of circles. Why it should bend like an arc of a circle? This is what you have learnt in strength of materials. Note 1. M by I is equal to EI by E by R. So R is nothing but EI by M. If EI is constant, M is constant, then R is constant. If M is constant, then R is constant. R means radius of curvature is constant. For which curve radius of curvature is constant? It must be an arc of a circle. It means that it is an arc of a circle. Now also we have studied that pure bending moment cases, M need not be constant. M can change, but still it can be a case of pure bending moment. What you have learnt? Supposing that if you have a cantilever beam subjected to a uniformly distributed moment like this. This the beam say moment is small m kilonewton meter per meter. This the bending A, B, let us say. This length of the beam is L. What you have learned in strength of materials? The bending moment diagram is what? Constant or rectangle or triangle. See here, for 1 meter length, m kilonewton meter, L meters, m into L. So it will vary linearly. This value is m into L. Stand here, look right side, no moment. So bend moment is 0. So but here it is m into L. Since L has power 1, it varies like a straight line. This is your bending moment diagram. For a cantilever beam subjected to uniformly distributed moment. Now, is it a case of pure bending moment or not? How you have decided? What you will do is, you will take a section, a small section like this, right? This distance, let us say dx. You take at a distance of x. Take that free body diagram of the beam. That free body diagram will tell you whether it is a case of pure bending moment or not. What we have to do? Cut here, pluck it out. When you pluck it out, it looks now something like this. Okay. This length is dx, subjected to a moment m. Free body diagram means it is the diagram of a body on which what others are doing you have to show. Okay. This is m kilonewton meter per meter. So we'll make it as say m. So total moment is something we can show. Now when I cut here and separate it out, what this free body or what this member will do on this you have to show. What right hand side of the member will do on this one is anti-clockwise movement. How much? That moment is m into x. For meter length m kilonewton meter, for x meters m into x. So when I cut here, what this is doing on that you have to show. So total moment is m into x and that will act on this one. Next, when I cut here, what this fellow will do on this you have to show. For that matter, what this fellow will do on this is anti-clockwise. In return, this fellow will exert on this clockwise. How much? Total moment is m into x plus dx amount of moment. This piece of the member will exert on this one. Why? To keep this element in equilibrium. This is free body diagram of element dx. So all forces, is it in equilibrium or not? Now you see, if I take the shear force also, assume that you are making shear force here, let us say. This is V, like this. Then since it is already in equilibrium, mx, this is m into dx, this is mx plus m dx. This shear force will be 0 here. This also will be 0. No shear will develop because you see, take moments of all forces. Sigma m, summation of moments of all forces is equal to 0. Clockwise positive, anti-clockwise negative. This is minus mx. This is minus m. Per length of dx is minus m into dx plus m into x plus dx. See, mx plus m dx. Already this became 0. So, since the element is already in equilibrium, V is equal to 0. We need not develop. If it is upward shear, it should be downward shear. If some shear is there, so then you cannot keep it in equilibrium. Because already in equilibrium, this couple is not required. Any additional couple is not required. So once the shear force is 0 in a cross section, in a beam, it means that it is a pure bending moment case. An element subjected to only bending moment is called pure bending moment. Whether the bending moment is constant or bending moment is varying, we don't want to worry whether shear is there or not. This is a case of pure bending moment where m is not constant. This is a case of pure bending moment where m is constant. So, this is pure bending moment where m is not constant. If m is not constant, then it will not bend like an arc of a circle because continuously bending moment is changing. So, m is not constant. So, r also will not be constant. That means it is not a the curve means circular arc. So, where m is not constant. So, r is not constant. So, it it is not an arc of a circle. So, what is your conclusion from this? If a beam is subjected to pure bending moment where m is constant, then it bends like an arc of a circle. Bends like an arc of a circle. Now, in this problem, both segments AB, BC bend like arcs of circles because bend moment is constant. Questions they ask in the exam is like this. They give you the cantilever frame. The segments which are subjected, which bend like arcs of circles are only BC, only AB, both AB and BC, like that. So first you have to see the bend moment diagram. If it is constant, then both will bend like arcs of circles. You have to take it. So in the above problem, both segments, that is AB and BC, AB and BC bend like arcs of circles. So both will bend like arcs of circles. Now, it is not necessary that we should have a straight member. You can find bending or deflections in curved members also. Then you have to take strain energy stored in the curved member, not straight members. So accordingly, strain energy stored in the member dx we should not write elemental length, ds curved element we have to take it and find the energy and also deflection. Let us see one such problem. Now you see delta vertical displacement of B. We will take now a curved member like this. Assume that you have applied a load W. This point, let us say A, B. This is the radius of curvature, let us say R. Okay, EI is equal to constant. Now you have a quarter circle or quarter circular segment whose EI is constant. You are applying a vertical load W. We want to find vertical displacement of B. Okay, first let us see what is the scope of the work. Delta vertical displacement of B is equal to integral of mx into m. Now elemental length cannot be dx because straight member you should not take, curved member you have to take, and what is the energy stored in that curved member, you take it and integrate between the limits. So mx into m into ds by ei. ds because strain energy stored in the curved member should be considered. So mx, bending moment at xx due to applied loads. M means same again, bending moment at xx due to unit vertical load. Unit vertical load applied at B. So this is the scope of the problem. Now let us see how we should write the solution. Mx and m values. Now table as such not required. First step, mx and m values. This is the load W. This point let us say A, B. This is your mx diagram. Then small m diagram means unit vertical load means 1. Here 1 you have to put it, and this one has no units. This point again A, B. Now what is the meaning of taking a curved element is like this. From the wherever the beginning and end of the arc, when you drop the normals, they meet here. Now you take a section xx here like this, and another element here, another section. This curved element is ds, nothing but r into d theta. This radius is r, this angle let us say theta, this small angle you take say d theta. Okay. Now dx is horizontal straight member. Now ds is a curved element at xx and again at a distance of d theta one more. at an angle of theta, you cut it. That is xx. Theta plus d theta, cut one more cut. Then between the two sections angle is d theta. Like x plus dx you write it, two cuts will make it. Here theta plus d theta, two cuts you have to make it. In the process you get a small curved element ds. That ds length is r into d theta. Okay, that's how we have to cut it. When this radial line cuts the section xx, wherever it cuts, here it is cutting, from here to the line of action of the load, this becomes x. X now becomes nothing but r sine theta. In the same way, here also you have to cut it. Section xx, wherever it cuts, this distance is x. This angle is theta. Okay. This is small m diagram. Since only one element is there, table is not required, directly we can get it. So mx is nothing but stand on the red color dot, look at the w. W into x minus w into x. X is nothing but if this is r, this is theta, this is r sine theta. W into r sine theta. Then small m minus 1 into x. So minus 1 into r sine theta. ds also we know r d theta. So delta vertical displacement of B is mx into m into ds by ei. If you forget that instead of ds you write dx, say when you integrate dx, put limits 0 to r, you will get a cantilever beam of length r. But whereas it is a cantilever beam of length pi r. So to that extent error will come in the deflection. So integral of mx minus w r sine theta small m minus r sine theta ds r d theta by ei. Now limits of integration for theta is theta can be 0. If I turn it like this, the d theta I can take here, then theta becomes 0. D theta if I take here small element, then it can be 90 degrees. So 0 to pi by 2 radians. So r you can take it out. W r cube by ei 0 to pi by 2 sine square theta d theta. So this is simple integration, we know wr cube by ei. Sine square theta means theta by 2, 0 to pi by 2. So you will get wr cube by ei into pi by 4. This question they have asked in engineering services, civil services, GATE, every time, repeatedly they asked many times. One time they asked vertical displacement, horizontal displacement. Same question, sometime they ask alpha into WR cube by EI, where alpha is pi by 4, pi by 3, pi by 2, like that. So alpha becomes pi by 4. Means this quantity is pi by 4. WR cube by EI is constant they give. So like this, if you have a curved element, not only here whether you take strength of materials or structures, wherever you take it, that strain energy stored in the member you have to take it. If it is a curved member, curve equation we should know. Then only you will know exact energy stored in the curved member. So this is about the cantilever frames. Either it can be straight or curved. Now let us see simply supported frames. Remove this one. Now delta horizontal displacement of the joint D. Now we'll take a simply supported portal frame A, B, C, D. Assume that subjected to a central load of 10 kilonewton, 4 meters to I, 4 meters to I, 2 meters I. Now you see, first of all, what you have to decide is it's a statically determinate frame. One end hinge, one end roller. So unknown reactions are three reactions we can find. Only such problems we can manage in the exam in 1 minute time. Okay. Now, since it is a statically determinate frame, now we can find. Now, what is the scope of the work? Horizontal displacement of joint D is equal to, because a straight member, I can write mx into m into dx by EI, where mx again stands for bending moment at xx due to applied loading. Then small m, bending moment at xx due to unit horizontal load. Where you have to apply horizontal load? Applied at D. So first step you draw this one mxm values, then in the second step multiply them. Now you see, this is how you have to manage. First step, mx and m values. Now you see, you take a same beam, this is load is 10 kilonewton, this is A, B, C, D. This point let us say E, you take it, E, 4, 4. Okay, this is your mx diagram. Okay, due to applied load, then due to unit load. One. This one has no units. Again A, B, E, C, D. Same length, 2 meters, 4 meters, like this. This is small m diagram. If it is a statically determinate structure, simply supported, if they have to give us, it must be symmetrical one, like this. Or only two members should be there. Otherwise, the time will not be sufficient to complete the problem. Finally, in the exam, not more than two members you have to manage. Now, mx and m values. First, we will find, because they simply supported portal frame, you must find the reactions. If loading is not symmetrical, frame is not symmetrical, you have to find the support reactions also by writing sigma x, sigma y, sigma m. Then it will become a 20 marks question. Loading, structure, if they are not symmetrical, it will be 20 marks. If symmetrical, 2 marks. Why? See, by inspection itself, you can get the reactions. You don't have to calculate. VA is 5, VD is also 5. Horizontal reaction at A is 0. So over. See here, this applied load, one right. To balance it, HA is equal to 1, one left. Now because now sigma x 0 happened, Because the A and D are at the same level, the action reaction together will not form any couple. If A is here, D is somewhere here, say, then 1 and 1 will be there, but those two will form a couple. And so, to balance that anti-clockwise couple, clockwise couple in the form of VA and VD will develop. Upward VA, downward VA. Now that with horizontal reaction at A, it is already developed, and it is in equilibrium. Now vertical reactions will not develop. If vertical reactions also develop, who will balance? No vertical load is there. Then if I put VA 1, suppose VA down I put say, but those two will form a couple. Nobody is there to balance. So VA and VD have no choice other than becoming 0. So VA will become 0, VD also becomes 0. Like that by inspection you can find. Now Mx and M values. Always we will stand inside the frame. Stand here. To decide which member is sagging, which member is hogging, you go inside the frame and stand, look at this way, look at this way, look at this way. Suppose one more bay is there, say, then don't look left, look right side only. Start from here, you start right side only. Move, look right side only. Then the sign conventions of Bendman sign conventions already will match. Okay, here also you have to stand here. Now you see, how many segments we have to take? I can take a section XX here at a distance of x. Here I can take XX at a distance of x. It is enough to take only two segments because it is mirror reflection, symmetrical. HA is 0. If I know the strain energy of this one, same is here. If I know this, same is here. So find the strain energy and deflections due to these two members and multiply by 2. This contribution will come because of the symmetry of the structure, symmetry of loading. Member forces, bending moment, everything mirror reflection. So two members only we have to calculate. If you decide that 1, 2, 3, 4 segments you have to take it, immediately see the marks. It's only 2 marks. 4 in a table, 4 rows we cannot write. Time will not permit. Then you decide where they wanted to save our time. You will realize that it is symmetrical. Half is enough. Multiply by 2. Now you see, this is what we have to do. In the second step, delta horizontal displacement of D is integral of mx m dx by EI. Member mx m delta horizontal displacement of D integral of mx m dx by EI. Only two members will write. DC member first will take. DC member. Now DC member, go inside the frame, stand on the dot. Here, section right side you see. Section right side, how many forces are there? Only one, 5. But that 5 is passing through the dot. So bending moment is 0. So mx is 0. Now go inside the frame, take a section XX here at a distance of x. This must be x. Now go inside the frame, stand here, look right side. Section right side, one force is there. Any force that is acting upward will give positive bending moment. So when you are inside the frame, stand here, this force is like acting upward. If it acts like this, downward. So upward forces. So plus 1 into x. Since it is 0, it is also 0. Which means that the contribution of member CD to the horizontal displacement at D is nil. That is the meaning of that. Next, CE member. Stand here, look right side. 5 into x plus 5 into x. Next, take here. If you take a section xx here, here also you must take a section xx here at a distance of x. Now, stand here, look right side. VD already 0, 1 is there. Tail to the head towards the point. That point is here, dot. So, 1 into perpendicular distance is 4. Section right side anti-clockwise, it will sag. So, plus 1 into 4. So, limits of integration are 0 to 2 meters only. Mx is 5x, m is 4, mxm dx by ei. I as it is. Okay. So, two members are sufficient. This is 0. How much you will get? 5 into 4, 20. X square by 2. X means 2 square. 2 square by 2. EI. So, you will get 40 by EI. EC member. So, this entire thing multiply by 2. Why? 2, because of symmetry. Instead of writing the same lines once again and wasting the time, think multiply by 2. So, delta HD, horizontal displacement at the 2 into 40 by EI, 80 by EI. Now, here positive sign you get it. Positive sign indicates that delta HD is in the direction of unit load. That is, delta HD is rightwards, like that. So, in 2 minutes time, quickly we should draw these two diagrams and this one. Now, in this case, when you are calculating 0 to 2, you multiplied by 2. You have 0 to 2 you have taken multiply by 2. Instead of taking 0 to 2, 0 to 4 we cannot take directly. 2 times integral of 0 to 2 is not equal to integral of 0 to 4, because the curve is x square term is there. That means if I take 0 to 4 limits of integration, your Benjamin diagram will go like this, big triangle. But that is not the BMD. It's like a triangle, this triangle. So you must write 0 to 2 only. Whatever expression you get it, multiply by 2. It is not equal to integral of 0 to 4 directly. Be careful in the examination about that mistake. Now let us see how to draw BMD and the deflection profile. This delta HD is 80 by EI, that we have to just remember. Now note. Benjamin diagram and deflection profile. Now you see, if you take this diagram, the reactions you found, VA is 5, VD is also 5, HA 0. Okay. Now, you see bend moment diagram in the column CD. Stand here, loop down. 5 kilonewton will give 0 bend moment. That means in the column CD, in the column AB, bend moment is 0. This is A, B, C, D. Next, what's the bend moment at E? Stand at E, look right side. 5 into 2, 10. So 10, you mark it. Here it is 0, here it is 0. Because once it is 0, say up to here it is 0 only. So your bend moment diagram goes something like this. This value is 5 into 2, 10 kilonewton meter. Plus, this is 2 meters, this is 2 meters. So due to 10 kilonewton meters, WL by 4, we got again 10 kilonewton meter. We have learned that upward forces always give positive bending moment, downward forces will give negative bending moment. Now 10 kilonewton downward, what's the bending moment at E? Plus 10 you got. See, it looks as if there is an error. Downward load should give negative bending moment, but it gave positive bending moment. Where did we go wrong? It is like this. Due to 10 kilonewton, what's the bending moment at E? 10 into perpendicular distance how much? 0. That means 10 will not give any bending moment at E. Then who gave 10 kilonewton meter? If you stand at E, 10 kilonewton load bending moment is 0 only. Then who gave bending moment? This 5. 5 into 2. That 10 is because of 5, not because of 10. That clarity must be there when you are drawing the bending moment diagrams. So this is your bending moment diagram. Next, deflection profile. This point, let us say A, B, C, D. Now you see, again in strength of materials you have studied that in a segment of a beam, if bending moment is 0, that segment will not bend but it can rotate as a rigid body. In this case A, B, C, D, bending moment is 0, so they have to be straight, but they can rotate as a straight line only. They cannot have a curved shape. So because D moves right side, why? Just now we calculated AT by EI. All segments will move right side. Let us see. AB member before that straight bend moment is 0. That means it should be a straight line only like this. B will go to B dash. B goes to B dash. It is a straight line. Now to maintain that 90 degrees angle, it has to bend like this. C will go to C dash. Like this. Or you can say this way. C goes to C dash. It's a curve. Now then D will go to D dash. But to maintain 90 degrees line again, it will go like this one. D will go to D dash. This is also straight line. Now 90-degree angle maintenance means why should it there rotate is because of this reason. In an attempt to maintain this 90 degrees line, because bending to maintain 90 degrees it has to bend and maintain that 90 degrees. Now you see 90 degrees maintained. Okay, like that. So what degree curve it is? Due to point load, deflection curve is always third degree curve, or we can say third degree parabola. Then what is the deflection? YE. Sir might have told you simply supported beam central deflection is WL cube by 48 EI. W is 10, length is 4, WL cube by 48 EI. So 4, 16, 3. That means 40 by 3 EI. Like that. They can ask you any quantity. What is the central deflection at E? Or what is the horizontal deflection at D? Okay. This way we should manage the problems. Okay. Next. Why the third degree curve is this one? Any beam, supposing that you have a cantilever beam, load W, section XX at a distance of X. So bending moment at XX is minus W into X. So it is a first degree curve. Now you can, to find the deflection, you have written like this: EI d square y by dx square is equal to minus mx. So plus wx it will become. Minus mx we write because when you take y axis downward, if you take y axis downward, this minus mx you have to write. Because positive bending moment produces negative curvature, means reducing curvature. So that's why it becomes minus. I think those fundamentals are over. So wx. Now if you integrate, what will get? EI dy by dx, you will get wx square by 2 plus some constant of integration. Again integrate, you will get EI into y wx cube by 6 plus c1x plus c2. So what degree curve it is? Third degree curve. X cube is there. So what you understand from this? If bending moment is first degree curve, deflection will be 2 degrees extra. If bending moment is UDL is there, suppose. So bending moment means wx square by 2, second degree curve. Then add 2 more degrees, deflection curve you will get. Deflection curve degree you will get. Okay. So due to point load on the beams and frames, deflection curves are third degree curves with the exclusion of arches. In the arches, the influence line diagram itself for horizontal thrust etc. fourth degree curve you will get, because the for the indeterminate structures, integral of that mx square dx by integral of y square dx when you are taking and simplifying, horizontal thrust you will get x to the power 4 terms in the indeterminate structures. Determinate anyhow straight lines, indeterminate structures fourth degree curve you will get. That is for the stress functions. Here for a cantilever, though it is a statically determinate structure, if you draw ILD for the deflection, you will get a third degree curve. You replace W by 1, see x cube terms you will get. That means a third degree ILD you will get for the deflection. Okay. So beams and frames, deflection curves are 2 degrees you have to add to the bending moment curve. So these are the points. Now let us see one more example. on the simply supported frame. Now in this case, because of the symmetry, instead of taking 4 segments, 2 segments you have considered. Sometimes they give you only 2 segments. Cut it, only this portion they can give as a problem. So that no symmetry, nothing, we don't have to worry about it. Now you see delta HC, EI value they have given 10 to the power of 6 Newton mm square, and 510. This is a problem. Only problem itself is half of that problem they have given ABC. No load on this one. Here they have applied a load of 50 kilonewton. This is 10 meters. This is say 5 meters. Now, because now 2 minutes time only is there, you must finish off, try to finish off in 1 or 1.5 minute time. So scope of the work, that stories are over. Directly problem I am taking. First step, mx and m values. This is 50 kilonewton. This point let us say A, B, C. 10 meters, 5 meters. Now to find the support reactions in the exam, sigma x0, sigma y0, sigma m0 type stories we should not write. By inspection we should get it. For the trusses I have explained, same thing. Now you see 50 right. To balance it, 50 left. So here this reaction is 50 left. Now you see 50, 50 will form a couple. 50 into 10, 500 anti-clockwise. To balance anti-clockwise 500, clockwise should develop. See how my fingers are moving up, down, clockwise, upward, downward. This moment must be 500. Already distance is 5. That means force must be 100. 100 into 5, 500. Like that. So, plus 100 into 5 minus 50 into 10. They balance. This is MX diagram. Then M diagram. Unit load we will put it. A, B, C. 10 meters, 5 meters. Now, if you put 1 here, it has no unit story, also not required. 1 means here also 1. 1 into 10. So, that means this is 2. 2. VA is also 2. No units. Next, section XX. For this AB, you take XX here at a distance of x, because 100 into x is easy for us to manage. For this one, you can take section XX from here. It is our choice. From wherever you want, you can take it. Whichever side is easier, that side onwards you will calculate. Once you take here, here are no choice. Same thing you have to take it. X, X. Now in the second step, delta horizontal displacement of C, integral of mx m dx by ei, member mx m mx m dx by ei. Once they asked in GATE, it has a 2 marks question. So first you take the member AB member, stand at x, look left side. 100 into x plus 100 into x. Stand here, 2 into x. Limits of integration are 0 to 5 meters. 100 into x into 2x dx by ei. 100 into 2, 200. X square means x cube by 3. X cube means 5 cube by 3 ei. So you will get 5 into 5, 25 into 5, 125 into 2, 25,000, 250 into another 25,000 by 3 ei. Further simplification, don't do it, keep it as it is. Then CB member. So here you have to take. Stand here, look this one. This is plus. Because when you are standing here, section right side, this is like an upward force. It will produce positive bending moment. Plus 50 into x. Here 1 into x. Limits of integration are 0 to 10 meters. 50x into dx by ei. 50, take it out. X square means x cube by 3. That means 10 cube by 3 ei. So you will get 50,000 by 3 ei. So these are the individual contributions. They see to it that you don't require calculator also, but even if you require, quickly you can manage. So delta horizontal displacement of C, 75,000 by 3 ei. In other words, 25,000 by ei. Ei value has given 10 to the power of 6 Newton mm square. This you are got in meters. Newton mm square. 10 to the power of 6 Newton meter square it must be. So if I take 10 to the power of 6, this you take it as Newton meter square. Everything now is in meters, right? So, but this will become in kilonewton. Load is in terms of 50 kilonewton. So that means it is Newton mm square only. So you will get 10 to the power of 6 if you write it. Newton kilonewton meter square if I take it. So this value will get 0.025 meters. This value, I think 10 to the power of 6, it is kilonewton meter square. This value is 10 to the power of 6 kilonewton meter square. Now you will get here this value in meters. Now you can convert it as 25 mm. Okay. So this way, this is the scope of the problem. Okay. So this is about the deflections of statically determinate frames. Okay, next we will see the analysis of indeterminate structures by moment distribution, slope deflection methods, and later on matrix methods of structural analysis we will take. Okay, today we discuss the seventh topic, analysis of indeterminate structures. In these indeterminate structures, we take continuous beams and frames. Continuous beams and frames. In this analysis of indeterminate structures, we learn three methods. First is moment distribution method. Next, the basis of moment distribution method is slope deflection method. Next, we take the matrix methods of structural analysis, where stiffness matrix method, the basis for stiffness matrix method again is the uh, slope deflection method. So for all the stiffness methods of analysis, slope deflection method is the basis. On that, successive approximation is the moment distribution method. Matrix form is the matrix method of analysis, stiffness matrix method of analysis. So first we will take the moment distribution method, okay, then slope deflection method, then in the end we will take the matrix methods of analysis. So in this first topic we will take the moment distribution method. This moment distribution method is developed by Hardy-Cross. This moment distribution method is based on 5 basic concepts which we have learned in strength of materials. So first we learn those fundamentals, then on that basis how the moment distribution method is derived we will see. First concepts. First thing you should know is carry over moment, COM. Carry over moment is a reaction or a reacting moment developed because of the applied moment at the other end. So it is the moment developed at one end due to applied moment at the other end. Okay. Now let us see the case 1. When far end is fixed, carry over moment, COM, we have studied this as m by 2. Then how to get this m by 2? This we have taken here a propped cantilever. It is not necessary that it is a pin support. It is a joint where it can rotate. That's all. It can be hinge support or roller support or a rigid joint. At that point, you apply some moment M, then the share of moment for the span AB, let us say M. If it is a rigid, B is a rigid joint, let us say, where 3-4 members are acting. Then when you apply some 10M or something like that, out of 10M, moment at B for the member BA is M, let us say. That's what is applied. Or you take a property cantilever itself, where you applied, where only one joint, only one member is there. Joint B should not deflect. That's the only condition in this case. This M is applied moment. You applied this moment M. Because of that moment, the deflection profile of this beam is something like this. Like this it will deflect. Now to make the slope 0 here, some reaction must develop, otherwise slope will not be 0. This value MA, this is the developed moment, is M by 2. Later on we will prove why it should be M by 2. We take the help of moment area method to prove that to make that theta A 0, M by 2 moment has to develop. Otherwise slope will not be 0. This moment is called carryover moment. It is called COM. It is a reacting moment. This reacting moment is exerted by the fixed support on the beam. It is exerted by fixed support on the beam. Why? To make the slope 0. So it is developed by, or it is exerted by the fixed support on the beam to make the slope 0. So that's why it is theta A 0. We'll see later on why it should be M by 2. Now how to fix the direction of M by 2, why it is anti-clockwise? This is how you have to find. To find direction of MA. Not only this problem, any problem direction you have to find it like this. First, permit the slope to happen. This is applied. When you apply this much moment, the deflected shape of the beam is like this. So like this, let theta A be existing. This is theta A. Now what is the purpose of the fixed support at A? AB. Now at the fixed support, slope is not possible. Now what the slope fixed support should do? It should try to make the slope 0. If you think that applied moment is anti-clockwise, that's the action. Now reaction, if you put say clockwise, then what will happen? Clockwise moment when you write it, then theta A will increase. It will not decrease. The purpose of the fixed support is not to keep this fellow in equilibrium. Means anti-clockwise means I have to apply clockwise is not the purpose of the fixed support. The purpose of the fixed support is to make the slope 0. Now this is actual beam, let us say. Now this fellow came here, he wants to make theta A 0. How you apply this moment? Clockwise or anti-clockwise, this fellow will not worry. His purpose is to make the slope 0. Because you applied anti-clockwise, if this fellow gives clockwise, theta A will not become 0, it will further increase. So to make theta A 0, what this fellow should do is it should come here and press him up like this. Then theta A becomes 0. So this fellow must exert a moment like this. Then what will happen when you press it up? The deflection profile will go something like this. And that profile we have shown here. Okay. Now applied moment, reacting moment are in the same direction. M is anti-clockwise, MA is M by 2, that is also anti-clockwise. Then how to balance it? There is a net moment of 1.5 m. M plus M by 2 is 1.5 m, anti-clockwise. Then how to keep it in equilibrium? Then the two supports will offer an clockwise couple to make the moments 0, like this. VA, VB. So total moment is 1.5 m. So by L. 1.5 m by L up, Vb is 1.5 m by L down. Now you see this beam is completely in equilibrium. Sigma x 0, sigma y 0, sigma m is also 0. But what you don't know is why it should be m by 2. We will take from the compatibility condition. As in strength of materials you have studied, theta A must be 0. To make theta A 0, how much should be m by 2? So we take the help of moment area method, we will prove that. Once first the fundamentals are over, then we will prove why it should be m by 2. So this is the first case. When far end is fixed means, supposing that you stand here. Now for you it is near end. Come here, you have come far. Now it becomes far end. So how to decide whether it is far end or near end? If you go to near, it is near end. Go far, it will become far end. Whether it is a near end, far end is determined by this one. Applied moment. Who applied the moment? We only have to apply. When you are applying the moment, where are you? We are here. We are here and applied this much moment. Now for us that becomes far end. If such far end is fixed, where this doesn't deflect, then m is carryover moment is m by 2. It behaves now like a propped cantilever. Once a propped cantilever deflection profile is drawn, whether you have a hinge support or roller support or a rigid joint, we don't have to worry because it's a shear we know. So if you know the deflection profile corresponding theta A or theta B or slopes or the deflections, everything you can match. That means you can, from strength of materials, whatever values we know, you can simply attach them. You don't have to again derive and waste the time in the exam. So this propped cantilever profile it is. Okay. So now this is how it goes when far end is fixed, carryover moment is m by 2. Second case, when far end is hinged, carryover moment is 0. Why carryover moment should be 0? Carryover moment, you must think that it is a reaction. When far end is hinge reaction is 0. So that means carryover moment is 0. This is what you have studied in strength of materials. Supposing that you have applied a moment here. This is m. This is your applied moment. You went and applied this much moment. A, B. So when you apply this much moment, the deflected shape of the beam is like this. This theta A, there is no one to make this theta A to 0. Hinge supports are free to rotate. At that hinge support, beam is free to rotate. There is nobody to make the slope 0. So there is no one to give an anti-clockwise moment to make the slope 0. So the reaction is 0. That means carryover moment, because of that applied moment, is also 0. Carryover moment is nothing but the reaction developed because of the applied moment at the other end. So only when the moment is applied at the end, at one end, how much reaction is developed at the other end, that we call it as the carryover moment. So that reaction we call it as carryover moment. From SM we know there is no reaction. That means carryover moment here is 0. So here MA is equal to 0. That means reaction COM is 0 because slope need not be made to 0 by anyone. So that's all. That is the reaction. That is the carryover moment. Now let us see the third case, case 3. For cantilever beams, when moment is applied at free end, carry over moment, you will get minus m. Why carry over moment minus m? Because of this reason. Assume that we have a cantilever beam, a moment m you have applied like this. This is your applied moment. This point let us say A, B. Now, when you apply moment m, you see my fingers, observe carefully how my fingers are moving. You are applying a moment m like this. Because of that moment, will the B go down or up? See, moment is acting like this. See, for example, I explain here. This is a cantilever beam. I am applying moment like this. Will it go down or up? Supposing that if you think that it goes down like this. Now check. Stand here. Section right side anti-clockwise. Will it sag or hog? Section right side anti-clockwise moment is a sagging bending moment. That's what we have studied. So once we are telling that it is sagging moment, but you are showing hogging, that means it is wrong. So how it will deflect? When you apply moment M like this, it will sag. It must sag. For it to sag, it should go up only. Now this is sagging moment. So deflection is now upward. So that's how we have to resolve the issue. Apply the moments, then you see whether it will sag or hog. Is it sagging moment or hogging moment? Then accordingly force the beam to sag or hog. In the process it may go up or go down, whatever it is. So now you find that because of this moment M, this beam should deflect upward like this. Okay. This delta also we know. This point let us say B dash. This is YB. Strength of materials are told you this value is ml square by 2EI. Theta also we know. Theta B is ml by EI. Now the moment will develop like this as a reaction MA. This also we know M. So you see here, to make theta A 0, first permit the slope to happen, then it's like a straight line. Right? Now to make the slope 0, fixed support must apply moment like this. In the process, this moment is opposite to the applied moment. This is anti-clockwise. Now to make the slope 0, it is acting clockwise. Okay, fine. Let it act clockwise or anti-clockwise, but slope should be 0. Okay. So this is now COM. Because applied moment, carry over moment always are in opposite directions, for cantilever beams you must write minus M. Okay. So that's why minus M you have written. COM is negative because applied moment and carry over moment. Carry over moment means reaction. Carry over moment are always opposite to each other. For cantilever beams. Okay. So this is your third case. Now let us, you see now the deflection profile M, M. It is like an arc of a circle. So only two moments are acting. Same M will be now here. If at all you see any other problem with any other end conditions may be there, M and M are there, profile is like this, immediately the deflection has to be ml square by 2EI, theta B has to be ml by EI only. See, with entire same deflection profile, I can get with two different support conditions. This I remove. Now let us see case 4. When far end is a guided roller support, carry over moment is also minus m. See why it should be minus m. Let us see, we have a guided roller support like this. Okay. This point let us say A, B. When far end is guided roller support means you are applying moment here. This is M. Now when your applied moment is M here, that means you are here. Now for you that is guided far end. If such far end is a guided roller support, guided roller support is nothing but a movable fixed support. This can move up and down, but slope is 0. It's like a fixed support only, but not held in position, but effectively restrained in rotation. If it is effectively held in position and restrained against rotation, it is like a fixed support. But if it is not held in position but effectively restrained against rotation, that is called guided roller support or a movable fixed support. Fixed support only, but it will move up and down. Slope will be 0 only. Now the deflection profile, if you write it, see here, because of this moment, the deflection profile, it will be like this. Because it has to sag. See, stand here, M, everywhere M only, so it must sag only. This is a B comes to say B dash. Let us assume that this displacement, say YB. Okay, this is say theta A. Now, you applied M here. Can vertical reaction develop or not? Similar to that, supposing that if the vertical reaction develops, suppose upward force should be balanced by downward force, but there is no downward force can develop. A roller support cannot give any reaction parallel to the plane of rollers. So vertical reaction here not possible. If VB is 0, VA has no choice. It has to be 0 only. Then who will balance this M? This M. This M. This is now called COM. Now you see completely it is in equilibrium. Because VA because VA has to be 0, this is also 0, VB has to be 0. That means these two must be in equilibrium by themselves. Now you see M, M. In this case also cantilever beam case, M, M. No loading in between, no loading in between. This is like a deflection profile, is a cantilever deflection profile. That is also like a cantilever. Only difference is in the cantilever and this one, fixed support was there and it went up. Now this remained here only, fixed support went down. Other than that, no difference at all. Deflection profiles match. If deflection profiles match, you can simply add all the known slopes and displacements also here. That means in this case, YB has to be ML square by 2EI. This much amount it will come down. Theta A has to be ML by EI. Because this profile is like a cantilever beam subjected to movement at one end. This is like a reaction. No reactions developed at the hinge support. If VA is 0, it's like a free end. At the free end also no reaction. No horizontal, no vertical reaction. Here also no vertical reaction, no horizontal reaction. M is applied. At the fixed support, only one moment is there, no vertical reaction. So it is like a fixed beam, it is like a cantilever beam subjected to a moment M. So everything will match. M, this M also will become carryover moment. When you apply clockwise, it becomes anti-clockwise. So COM becomes minus M. Minus because same reason. If it is clockwise, it has to be anti-clockwise. Otherwise, that segment will not be in equilibrium. So, for cantilever beam, when a moment is applied at the free end, or when a guided roller support and hinge support is there, when a applied moment is at the hinge support, behavior is same. So, carryover moment is also same. Okay. Now, supposing that if you take a case like this, cantilever beam is there, you apply load W. This point, let us say A, B, length is say L. Now the reaction will develop MA is nothing but W into L. This is also reacting moment. That is also reacting moment. But this reacting moment you cannot call it as COM because this is not developed because of any moment here. It is simply reacting moment, that's all. If at all that reacting moment is due to applied moment, then it has a special name called carryover moment. That means all carryover moments are reacting moments, but all reacting moments are not COM. Okay, it is a reacting moment, not COM. So, COM is defined only when one end is subjected to a moment. Okay, so all carryover moments are reacting moments, but all reacting moments are not carryover moments. Okay, so now carryover moment you have complete picture. Carryover moment means it is the reacting moment developed because of applied moment at one end. Depending on the end conditions, that carryover moment can be m by 2, it can be 0 or it can be minus m depending on the end conditions. Purpose of carryover moment is to make the slope 0. This is first point, not one. Let us see how this guided roller support behaves, how actually the construction will be. Second point, structural behavior of a guided roller support. Let us see, it can be this way or whatever direction we want, we can keep the roller. This point, let us say A, B. Some length L, let us say. This is actually steel plate, a rigid steel plate. To the rigid steel plate, this steel column is welded. And below the rigid steel plate, you have too many rollers. Below the rollers, there is a support, fixed support. Means a support which will rest, which will take the roller reactions. On the sides, you visualize that there is a channel section. This is the rigid plate, let us say. Column is here, welded here. This plate, to prevent this type of rotation, there is a channel like this. Like that channels means, if you see the table drawers, on the table drawer sides you will have two channels, and too many rollers also will be there. On the rollers only your draw will roll. You can move the draw forward, backward, that's all. You cannot lift the draw because on the sides channels will be there. This draw will go and hit the top channel like this. Push it down, it will hit here. So it can move forward or backward. It cannot move up or down because channels it will hit. So this draw is guided to move only in one direction. Means either forward or backward only. You cannot rotate it, you cannot lift it. Okay. So that's why it is called guided rollers. That means rollers are guided to move only in one direction. Here also same thing. One channel will be, instead of channel like this, we have a channel like this, plate this way. It cannot go up because the web flange of the channel will stop this upward movement. So this will go and hit the channel flange. Here also the base will be there. Now you see, assume that we are applying a clockwise movement M. This is applied movement. So on the column there is some applied movement M, say. Now what happens? If at all there is nothing here, when I turn it up, naturally it will simply go up, this will go down. So simply it will move up because there is nobody to prevent it. But here what happens? There is a channel here, flange. That flange pushes him down like this with a force F. So who gives this F? It is exerted by flange of channel on the rigid plate. Now here this ground will exert an upward reaction. Actually that pressure variation in some fashion. Even if you see the table draws, not a single roller, there is a series of rollers will be there here and here. So they form a couple. The forces acting on the force exerted by the flange on this roller may be force, on this less force, less, like that it will vary linearly. But resultant force F somewhere here downward, say upward here, say. This will form a couple. This distance, some distance d, say. Okay. This force magnitude also F. So when you apply moment M, anticlockwise couple will develop by the flange of the channel, one force, by the ground, another force. So this will form an anticlockwise couple. Since we do not know this perpendicular distance d and what is the magnitude of the resultant force, but F into d we know. Moment at B is F into d. See, whenever I told you in the earlier classes also, whenever you show a curved arrow mark, it means that there must exist a couple like this. Without such a couple, this curved arrow mark cannot exist. Here, when we show a curved arrow mark here, there must be a guide. In that only it should roll. So when I hold it like this is anti-clockwise. So how it will exert when I am pushing it down? So this force will be, this flange will exert a force like this. This will exert a force like this, F and F. So F into D is some M. that anti-clockwise movement is m. So like that, force will develop. This will try to rotate like this, but this channel will press it this way. And when it is pressing here, it will try to come out. It will try to go right side. This rollers will try to go right side and this will press it opposite direction. So anti-clockwise movement will develop. These red color forces are the forces exerted by the flange of the channel here, here the ground or a wall, whatever it is. So that's why it is called free body diagram of the beam, because on the beam what flange of the channel is doing you have shown, what ground or wall is doing on the beam you have shown. Okay, so this is how the behavior of the guided roller supports. Guided roller supports will exert two reactions. One is a moment, one is perpendicular to the plane of the roller base, one reaction will develop. Parallel to the plane of roller base, it cannot exert any reaction, simply rollers roll in that direction. They cannot rotate, they cannot be lifted. Only in one direction they are guided to move. That's why we call them as guided roller supports. So now this is the complete information regarding carryover moment. Now let us see second concept, carryover factor. Second concept, carryover factor, COF. Now carryover factor means it is the ratio of carryover moment and applied moment. Now case 1, when far end is fixed, carryover factor is equal to carryover moment by applied moment. Carryover moment, just now you have learned m by 2, applied moment is m. So when far end is fixed, carryover factor is 1 by 2. Similarly, case 2, when far end is hinged, carryover factor means carryover moment by applied moment. In this case, carryover moment is 0, applied moment is m. So carryover factor becomes 0. Case 3, for cantilever beams, when moment is applied at free end, carryover factor is equal to carryover moment by applied moment. Carryover moment is minus m, applied moment is m. So carryover factor you will get minus 1. Same is the case with the fourth case. When far end is guided roller support, then carryover factor is equal to carryover moment by applied moment. This is also carryover moment, just now I told you, minus m by m, because both of them are identical. Other than the support conditions, deflection profile is the same, moment is same, so same carryover factor also we will get. Next, third concept is stiffness factor. I remove this one.